All right, so switching gears, accelerometers. Again, I posted the announcement about the app you can download on your phone so we can kind of demonstrate this real time instead of just you guys listening to me talk about them. Question first though, when you took physics, did you learn about relativity in intro physics? Okay, I see a bunch of heads, so no shaking. So even if you didn't learn this in physics, tell me if you've heard this explanation just kind of in popular science or somewhere else about how technically you cannot tell the difference between standing on the surface of the Earth in a uniform gravitational field or being off in deep space in a rocket accelerating at the same acceleration due to gravity. Have you at least seen or heard of this concept before in relativity, right? So I don't know about you, but this confused the hell out of me the first time I saw it. I was like, what, I don't know, that just seems weird. Like, how do you mean you can't tell the difference between those two things? And it didn't really click with me until I understood how accelerometers work. So that's kind of an aside, but we'll come back to it today. Maybe that's already obvious to you and you're like, yeah, that makes perfect sense, this guy's dumb, whatever. But for those of you who still kind of have trouble wrapping your heads around that, hopefully today will help. And then after the conceptual stuff, we'll talk about some kind of the practical things when it comes to using accelerometers. So again, forget the space thing for a minute. Say I just have a cantilever beam, right? This is something you saw in previous courses. Okay, it's on Earth, there's gravity, the beam has mass, so the beam is kind of going to deflect under its own weight, right? Another similar model for that is just a mass hanging on a spring, right? You have mass hanging on a spring, there's gravity, that spring is going to extend some length due to the weight of the mass. Okay, so that's, again, I'm just holding still in a gravitational field. And in both cases, let's say that the only thing I can measure or feel is the deflection of this beam or the extension of that spring. Okay, I do not have a camera or any external vision to see that it is bent or deflected. I don't have some little GPS tracker on the tip of the beam or on the mast to give me absolute XY coordinates. The only thing I know, okay, my eyes are closed. The only thing I know is whether that beam is bent or whether that spring is extended. I can measure that, but that's it. If that's the case, then I cannot tell the difference between, for example, putting that beam on a roller and accelerating it sideways. Right? The beam is still going to deflect if this cart is accelerating, or if I turn the spring and the mass sideways, and I grab the spring and accelerate sideways, the spring is still going to extend, right? But that is all I can measure. All I know is that this spring is extended. So I cannot tell the difference between accelerating in the x direction when there's no gravity, or hanging in the y direction when there is gravity, if that's all I can measure. Okay, so that's what this means, right? If I am standing on the surface of the Earth with my eyes closed, I can feel gravity, right? But if my eyes are closed, technically right now I could be in a rocket in space accelerating at 9.81 meters per second squared, right? Clearly there are other sensory things that tell me I'm still in this room. But if that was the only information I had, no GPS, no vision, I can't look out the rocket's window and see that I'm moving relative to the stars or whatever, then you can't tell the difference between those two scenarios. And this is leading into, okay, well, how do accelerometers actually work or detect acceleration? And why does that acceleration get conflated with gravity? And then what can you do about it if you just want to measure kind of true linear acceleration in a fixed reference frame like this where you're not moving? Okay, and again, there's a whole biology side to this where the human inner ear kind of has basically a biological structure that does this, right? Like I can close my eyes and tilt my head sideways and I can still kind of tell that that way is down even though I can't see that the room is rotated. And that's how you get into seasickness and motion sickness and all the things, right, where you're spinning around in circles to make yourself dizzy, where your kind of visual stimulus gets off kilter from what your ear is detecting and your brain gets all out of whack. Right, so again, that's kind of the conceptual framework. So any conceptual questions on starting out with this? No? Okay, so how do you actually do that with an accelerometer? So when I say accelerometer, I mean we want to have some device that actually measures this acceleration and gives us an electrical signal out. And there's different ways to do it, but a common one is capacitive, where, for example, kind of sketching a model of this, we do have a mass that's suspended between two springs, but on that mass is actually one movable plate of a capacitor, right? So then we are going to have some distance. Sometimes there's two plates, one on each side. So there's some capacitance C between, oops, sorry, off the bottom of the camera there, this middle plate and that plate. So these two outer plates are fixed, but this middle one moves, and the capacitance has this inverse relationship with distance, where it goes up as the distance gets smaller, right? So as that mass moves, we can measure the change in capacitance, and then there can be some other circuitry that eventually converts that to a voltage. Okay, so that's the electrical concept of, okay, how do we convert a physically moving thing to something electrical we can measure? If you look up MEMS, micro electromechanical systems capacitors, it's usually a more complicated comb structure, where there's kind of a movable thing that looks like this, suspended on springs, and then there's an outer set. So it's not just one pair of capacitor plates, but it's a whole bunch of them. So these outer ones are fixed, and the inner one is movable. This isn't an exact diagram, but you can go Google image search MEMS accelerometer, and you'll see tons of diagrams like this pop up. So all of these things are moving back and forth, and the capacitance of the whole thing changes as it moves, and then that's how we measure the acceleration. But again, same concept. I can't tell the difference between, if I just accelerate this thing sideways, the capacitance is going to change, and if I rotate it and that mass is just hanging under gravity, the capacitance is also going to change. So technically, if the sideways acceleration is exactly 9.81 meters per second squared, then the electrical signal I get out is the same in both cases. The other interesting thing about all of these cases is if I say take that mass or that cantilever beam and I drop it, okay, so say this end was fixed, but I just drop the whole thing so it's in free fall, then the beam actually isn't going to deflect at all, right? So I'm going to measure zero acceleration. So the acceleration that accelerometers like this measure is called proper acceleration, which means relative to free fall. So if I, again, measuring linear acceleration in a fixed Earth reference frame relative to the ground, if I drop this, I'd say it's accelerating down at 9.81 meters per second squared. That means if I have an object just sitting, and we'll see this with the phones in a minute, if I have an object just sitting on the ground, it is going to measure an upward acceleration of 9.1 meters per second squared, because that is relative to a freely falling object, not relative to the fixed ground. Okay, and again, same thing would apply to the mass here, right? If I just kind of drop the mass in the spring, then the spring isn't going to stretch because the upper part isn't being held in place, right? So the whole thing's just going to drop and the spring isn't going to expand. Okay. Questions? All right. So what I want you to do now is pull out your phone and open one of those two apps that I suggested. Either the first one, I don't know how to pronounce this, FIFOX, something, physical phone experiment is what it's supposed to be short for. So I'm going to use this one as an example, but again, you could use Physics Toolbox, it's very similar, or if you downloaded another one. So your phones have all sorts of sensors built into them, right? And these apps just give you easy access to the raw sensor data. So I'm going to go to acceleration with G. So this is the one that includes gravity instead of trying to subtract it out, which we're going to talk about later. I'm going to go over here to the multi tabs. I'm going to get glare. I wonder if I turn this light off, if that's better or worse. Yeah, it's actually kind of cool. Okay. So if I hit start, I can see it's just kind of recording all three accelerations, right? But so X and Y are 0, but if I shake it side to side or up and down, okay, see, then I kind of got those oscillations in x and y, but even when it's just sitting still, z is measuring roughly positive 9.8. So there's a little bit of noise, and my phone's not perfectly flat, but about 9.8, okay, not 0 is the point. If I pause that and go back out to acceleration without g, we'll talk more about how it does this later. Okay, then it's actually measuring 0 for everything because it's subtracting gravity out. Okay, the problem, or what gets difficult, the acceleration with g is, okay, what if and the motivation for kind of the back half of the lecture here, what if I wanted to use this for navigation? Okay, so I don't have GPS, I don't have vision or some external thing to reference where I am. Then you might say, hey, okay, well I can measure acceleration. Velocity is the integral of acceleration and position is the integral of velocity. So if I move my phone around, I should be able to double integrate acceleration and figure out where I am, right? The problem with doing that is that, as you can see, if your phone is not perfectly flat, then there's going to be a tiny non-zero component of gravity in either the x or y direction, right? And that is, since you're doing a double integration, that is going to accumulate really fast. I think I'm going to switch back to the document cam in a second here to work through the math. But basically, even if your phone is actually sitting perfectly still, after just a few seconds, accumulating that tiny error makes you think you're several meters away, because the double integration accumulates so fast. Okay, so you can kind of play with this, see what happens as you shake it around or as you tilt it, right? This is a little harder to, well, let me restart that. So this is a good example. For example, if I shake it back and forth like this, shake it a bunch, see how I got a big sine wave in the x direction here, but if I tilt it, I have my phone on, the screen's gonna freak out with auto rotate, but you get the idea. I also got oscillations in the x direction there, so can't differentiate between that side-to-side acceleration or, okay, now there's a gravity component in the x direction. Okay, so turning the light back on, that is not what I wanted to do. So trying to do, it's called inertial navigation. Also, we kind of talked about this. We were talking about the robot navigation right last time. Again, if my eyes are closed and I'm trying to just think, integrate acceleration to figure out how far I've gone, that error will kind of accumulate very rapidly, and I'm going to have a hard time walking around without crashing into stuff. So again, velocity is the integral of acceleration, distance is the integral of velocity, but that's a double integration if you're measuring acceleration. Let's see if I actually wrote down some numbers here. Yeah, so say you just have a 1 degree error, right? Like you think the thing you're measuring is perfectly flat, but it's actually tilted. I'm drawing this exaggerated, but by just 1 degree. So instead of 0 gravity component in the x direction, you have 9.81 meters per second squared times sine of 1 degree, which gives you about a 0.1712 meters per second squared gravity component in the x direction. That's actually pretty big, right? So if I think I did the math, after just 10 seconds, that's going to tell you that you have moved about 17 meters if your phone is literally just sitting still. So kind of a terrible way to actually track distance just by integrating acceleration, unless you know which way gravity is actually pointing. And again, if you think about how that error grows, we're just like sketching graphs of integrals back from calculus class. If your acceleration is flat, well then the integral of that is going to be linear, and then the integral of velocity is going to be quadratic. So the error grows not exponentially, but quadratically with time, which is still really fast, right? Okay. So how do you potentially compensate that? How was your phone doing the part where it said it was subtracting gravity out? We also have other sensors that can give us an idea of our orientation to figure out which way gravity is. Okay, so one of those is a gyroscope, which we're not going to get into the physics of how they work, but that gives you angular velocity, which you can integrate to get orientation. Okay, and so again, you need to know your initial position, right? You need to know, okay, my phone started out flat, but then once it starts out flat, you can integrate angular velocity to get your current angular orientation. You also have a magnetometer, which gives you orientation relative to Earth's magnetic field. Or nearby strong magnets, which are kind of dominating Earth's magnetic field. But assuming you're not near any other magnets, it's kind of safe to assume that the dominant magnetic field you're experiencing is Earth's magnetic field. So if you pull the app out again, you will see that your phones, turn the light off again, also have these, right? So I can go into gyroscope, look at rotation rate, which is, you know, a little noisy starting out there, but about 0. And then if I spin my phone around, whee. Okay, see how I had this rough, actually kind of a nice decay. So the X and Y rotation there was just noise, but the Z rotation, so about this axis, I actually had this nice initial peak, and then you can see it kind of slowing down with friction as the Z rotation slows down, and then I stopped it again, right? So I could integrate that to get angular position. Okay, and then you also have a 3-axis magnetometer in here, which again I should be able to spin around and basically acts like a compass, right? So we saw there, again, X and Y, Earth's magnetic field is mostly changing in this direction. I kind of got that nice sinusoidal oscillation in X and Y, and that's giving me orientation. So we're not going to get into all of the math of how it then does this. So you have 3 things, right? You have your accelerometer, you have your magnetometer, and you have your gyroscope. There are things called sensor fusion algorithms that will kind of take the inputs from all 3 of those things, ultimately give you, okay, which way is gravity right now, and then how do I subtract out the gravity vector to get actual linear acceleration. So that is why I can then go to acceleration without g. And here, even if I tilt my phone, again, there's a little bit of noise with me jostling and everything, and the screen is rotating all over the place, but I'm not getting those huge sinusoidal oscillations like I was when I was tilting it with gravity on. Okay? So a lot of this, and like early days of NASA when GPS didn't exist, like how do you know where the Apollo rocket is, that type of stuff. And the short-term application for you guys, is this worth doing on your robot? Probably not, because again, you have a well-defined arena with boundaries that you can detect. Okay, so rather than trying to integrate and say, okay, I know the board is 4 feet wide and I started on the edge, so I want to know when I've driven about 2 feet to the middle or whatever it is, it's easier to just use the color sensor and then you know exactly when you've hit the middle. Okay, but again, if you have a robot driving around in an unstructured environment, in addition to encoders, you also have this type of information to kind of give you an idea of your orientation and how far you've traveled. Okay, the next question is, okay, great. And Rob, I think this was getting to your question from last time. You want to use one of these with an Arduino, how do you actually communicate all that information to the Arduino? So let me do this on the 3rd page and turn the light is on. Is the light on? No, there it is. So there is a whole world of different communication protocols that we don't have time to get into in this class. So there is parallel communication, and this I think now seems, if you remember older, are you guys too old to, or sorry, too young to know what a VGA port is on a computer, like older computer? You do know what VGA is, like the older monitor? Okay, thanks, you're not that old yet. There's kind of older computer cables that always seem like they had a million pins on them, right? So this is when you have a port where there's a bunch of different data lines that are having kind of a whole packet of information. So if this is out bit 1, 2, 3, 4, 5, 6, I should have drawn a 7th one in there. And this is in 0, 1, 2, 3. I got messy with drawing the lines lined up with the numbers there. Basically, you're sending a whole byte at once over a bunch of different lines. That's parallel communication. And then you might also have to draw a clock signal in there, kind of synchronizing how that data is sent, as opposed to serial communication, where you have, in some cases, just one line sending kind of bit 0, bit 1, bit 2, bit 3, and so on. So this is out, this is in, and then there's also a clock signal. So this is really fast because you can send a whole bunch of data all at once, but requires more physical wires, whereas this is kind of sending one bit at a time. It doesn't require as many wires. There are a ton of acronyms. So if you ever, again, you're buying Arduino sensors, you're kind of hearing more about this. USB stands for Universal Serial Bus. SPI, Serial Peripheral Interface. I2C is integrated circuit. So these are all different protocols basically for how these bits are sent. And again, we're not going to get into all of the details of it today, but I kind of wanted you to at least have a vague idea of what these acronyms are if you encounter them in the future. For example, if I just want to send a single 8-bit number, right? So 0B something 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 something. Many times that if you hear about data packets, right, there will also be kind of additional leading or trailing bits with information about the packet, right? Like a start bit saying, okay, I'm going to start, I'm going to give you the numbers, and then I'm going to stop, or I forget what other information can be in there. There's error checking and all sorts of things. But point being, when you want to go buy something like an accelerometer and use it with an Arduino, many times there will be a library the sensor will be built for a specific communication protocol, and there will be an associated Arduino library that uses that communication protocol to get the data. Okay, that is in contrast to analog sensors, which we have talked about. You can also go buy an analog accelerometer that just gives you, so I should have clarified, this is all digital, where all of these voltages are either high or low, we're just transmitting ones and zeros. You can buy an analog accelerometer where, for example, the output, say 0 to 5 volts, corresponds to minus 2g to plus 2g, where again, g is gravitational acceleration, 9.81 meters per second squared. You can buy them with different ranges, right? Some accelerometers are going to saturate at different range, so some are better for measuring, say, very high accelerations like impacts, whereas some have a lower range but better resolution. So these are all, again, I'm assuming most groups are at the point where you're not going to do this with your robot, but I wanted you to know kind of roughly how they work going forward. Another note on language, when looking at documentation for this stuff, you might see the acronyms MOSI or MISO, which stand for Master Out, Slave In, and Master In, Slave Out. Thankfully, people realized, okay, we could probably think of a better thing to call those. Which of course you can't do without pissing off a bunch of old white guys who grumble about how we shouldn't have to change it and blah, blah. But I think the new industry standard is, for the most part, COPI, CIPO, which stands for Controller and Peripheral. So for example, if you look at the most recent Arduino documentation, like these terms have been updated, but they still have a note that says note these terms have replaced these terms. If you look at older data sheets for some random part you buy on DigiKey or whatever, you might still see those. Again, I want you to know what they mean, where again, these are referring to, okay, what's the controller is your Arduino, and the peripheral is the thing your Arduino is communicating with. Okay, so there is probably a whole bigger list of alphabet soup I could do here that I'm not going to go through all of, but I want you to have seen these terms, even if you're not going to use it in this class, in case you encounter going forward. Any questions? Again, other than kind of playing with the phone, I don't really have an activity, or we're not going to do any of that in Tinkercad or anything. Any questions? Yes? Oh, sorry. So range. So this one was voltage, and this is the range of the acceleration that it can measure. Okay, and that two is just an example, right? So where G equals 9.81 meters per second squared. Usually if you go buy an accelerometer, it's not going to give you the acceleration range in meters per second squared. It'll say something like plus or minus 32 G, or whatever it is. So you can even, not that I recommend dropping your phone, but if you, I don't know, shake it really hard. Okay, so you can see how that graph is still smooth at the top, so it wasn't saturating, right? Again, unless somebody wants to volunteer to drop their phone, I don't think we're going to try to saturate this, but that's a pretty big range, right? Like I was getting all the way down to negative 100 meters per second squared, so that's roughly 10 G, okay? So I don't know, if you ever want to get mad and throw your phone or something, turn the accelerometer on first and see what you get, but I'm not going to demonstrate that with mine. Okay? Other questions? Yes?
Is gyroscope going to interfere with magnetometers?
Is the gyroscope going to be interfering with the magnetometer? Not that I'm aware of, but I would need to look more into the physics of how both work. And I don't think the gyroscope generates a magnetic field or anything that would interfere with the magnetometer. But again, electrical currents generate magnetic fields, right? So I think that is probably getting into really deep ECE territory about like if you're going to have, there's a magnetometer in here somewhere, does it need to be located in a place where it's not affected by the other components in the circuit, or do you calibrate that or shield it somehow? I have no idea. You'd have to ask an ECE professor. But yes, more broadly, magnetometers can definitely be affected by other nearby magnetic fields. Like if it's just kind of out in space in a field somewhere, you just have Earth's magnetic field, but if you're near other things generating magnetic fields, then they can influence it. Like I didn't bring a permanent magnet, but I could have, rather than spinning my phone like that, I could have moved a magnet in a circle around my phone, right? And then since I'm so close to that magnet, its magnetic field kind of dominates Earth's magnetic field and it will mess up the magnetometer. Okay? Yes?
I will drop my phone for science if you're interested.
I mean, at least drop it on the carpet. I don't know. But yeah, go. I mean, I'm curious if you see what the peak. There's a hard table here. You can like stand on a chair if you want to go nuts, but.
This will be interesting no matter what.
Okay.
What is
What do you get?
I'm trying to pause certain shit. 120.
Okay. Yeah, and it's still. I mean, we'd have to like pause it to zoom in. It's pretty saturated. So, and I guess this this saturation concept isn't just for acceleration, right? Like we talked about accelerometers and other sensors. Most sensors are not going to have infinite range. Okay, so that's something to consider when temperature sensors are another good example, right? Like we care about temperatures on a human scale, right? But if you need to measure really hot or really cold things, you might saturate the temperature sensor, that sort of thing. Okay. Other questions? All right, it's nice out. Go outside. Short lecture. I got nothing else. Nope, no polling. Did you guys only come in case there was a poll? Not because you were excited about accelerometers?
Professor, you should roll